Hello everyone, in this video we will learn all about optimization in calculus. Given this graph with the intervals from A to D, this point here is considered as the absolute maximum because it's the highest height in the graph. This point here is considered as the absolute minimum because it's the lowest point in the graph. Well, this point here is considered as a relative maximum or with the local area at this point because you go up then down. So it's the relative maximum. Well, this point here is considered as the relative minimum with this local area at this point because you go down then up. So take note of that. Now, how to find the extreme point? So first thing first, solve for the derivative. Next, equate the derivative to 0 and solve for x. Next, substitute x to the original equation in order to find y. So this will be the critical point or points. Then solve for the second derivative. If the second derivative is lesser than 0, the function has a relative maximum at x equals c. But if the second derivative is greater than 0, the function has a relative minimum at x equals c. Now let's have an example. Now find the relative extreme value of the function. Now given this function, so the first thing we do is solve for the derivative. So getting the derivative, so that would be negative 2x. Derivative of this is 6. Next, equate the derivative to 0 and solve for x. So with this, transfer 6 to the other side, divide the equation by negative 2, so our x is equal to 3. Now substitute x to the original equation. So with that, negative 3 squared plus 6 times 3 minus 2. So simplifying, we will get 7. So with this, our critical point is actually 3 and 7. Next, solve for the second derivative. Now take note, the second derivative of negative 2x plus 6 is negative 2. So since negative 2 is lesser than 0, so therefore 3, 7 has a relative maximum. Now take note, when you sketch this, the graph for this is a parabola that opens downward. Downward because, again, the sign for A is negative. So with that, at this point, it has the highest or a relative maximum. So take note of that. Okay, another. Now find the relative extreme value of a function. So given this, so again, so this will be its graph. So take note, we're looking for the relative extreme value. So with this, first, find the derivative. So this will be 3x squared minus 18x plus 15. So equate that to 0. So divide the equation by 3, we will get this one. So factor this, we will have x minus 5 and x minus 1. So with that, our values for x would be 5 and 1. So next, substitute in the original equation. So f of 5, so simplifying, we'll get negative 45. Then f of 1, that would be negative 13. So with that, our critical points are 5 and negative 45, and 1 and negative 13. So with that, let's solve for the second derivative. So with that, this is our first derivative. To get the second derivative, this would be 6x. Derivative of negative 18x is negative 18. So with that, we will solve for f double prime of 5. Substitute, so we will end up with 12. So since 12 is greater than 0, so with this, it will have a relative minimum. Then for f of 1, we will end up with negative 12. So since negative 12 is lesser than 0, so therefore it has a relative maximum point. So with this, 5 negative 45, so that would be 5 negative 45 is the relative minimum. So this will be the point. So it's the low, it's opening upward. So relative minimum. At 1 negative 13, it has a relative maximum because it opens downward. So take note of that. Okay, so take note, this is relative extreme value. Now, let's have another example. Now, at this point, we will find the absolute and the relative extreme value of a function. Now, this is our equation with the endpoints from 1 until 4. So again, the first thing we do is solve for the derivative. So derivative of this is 2x, then minus 4. So equate this to 0 and solve for x. So with that, our x is 2. Next, substitute x in the original equation to find y. So that would be y is equal to 2 squared minus 4 times 2 plus 9. So we will end up with 5. So our critical point here is 2, 5. Now, get the second derivative. Second derivative here is 2. Since 2 is greater than 0, so therefore it has a relative minimum point at x equals 2. Now, since we're looking for the absolute and relative extreme value with the endpoints from 1 to 4, so making use of the original equation, so we will have here 1 as our first endpoint, and 4 is another endpoint, and we have 2 here because it's our critical point. Now, substituting 1 in the original equation, that's 1 squared minus 4 plus 9, we will end up with 6. Substituting 2 in the original equation, take note, we end up with 5. And substituting 4 here, that's 16 minus 16 plus 9, so we end up with 9. So take note here, 9 has the highest value for y. So with that, at 4, 9, it has the absolute maximum point because it's the highest. Now take note also that 5 is the lowest value for y. So with that, at 2, 5, we have our absolute minimum point, or it's the lowest point, and take note at the same time, it is also where our relative minimum point is. So take note of that. Okay, another. Find the absolute and relative extreme value of the given function with the intervals from 1 until 6. So again, the first thing we do is solve for the first derivative. So with that, derivative of this is 12x squared. Derivative of negative 39x squared is negative 78x. Derivative of 90x is 90. And derivative of a constant is 0. Now at this point, equate this to 0. Then divide this equation by 6, so we end up with 2x squared minus 13x plus 15. Now at this point, we will factor this, so we will end up with this one. So with this, the value for our x will be 5, and the other one is 3/2. Now getting the second derivative of this one, so derivative of this is 24x, derivative of this is negative 78. Now substituting x here by 5, so we will end up with positive 42. So since 42 is greater than 0, so at this point, it has a relative minimum. Okay, next. Now, substituting x here by our second value for x, which is 3/2, or that's 1.5. So we will end up with negative 42. Since negative 42 is lesser than 0, so at x equals 1.5, it has a relative maximum. So take note of this. If this is positive, it's actually minimum. If it's negative here, it's actually maximum. Now, making use of the original equation, let's make a table. Now, in the table, we will write the first here for 1, our first endpoint, and 6 at the other endpoint. So since we have here the values for 5 and 3/2, so we will just place it in between. So again, substituting 1 in the original equation, we will end up with 57. So you can make use of your calculators to countercheck that. So if we have 3.2 or 3/2 or 1.5, substitute here, we will end up with 62.75. And if our x is 5, substituting it here, we will end up with negative 23. And if our x is 6, we will end up with 2. Now take note here, negative 23 here is the lowest value for y. So at this point, at 5, negative 23, it's where the absolute minimum. It's the lowest point. And take note, 5 here, it has also where the relative minimum is. Okay, next. Then 62.75 is the biggest value for y. So with this, it's where the absolute maximum and at the same time the relative maximum is located. So take note, not all the time the absolute maximum and the relative maximum will go together, nor the absolute minimum and the relative minimum will go together. We really have to counter check. So please take note of that. Okay. Now, let's have this optimization problems. So let's have the first. Now, the sum of two positive numbers is 12. What are these numbers if their product is a maximum? So take note of this. The first sentence, the sum of two positive numbers is 12. So that would be s is equal to x plus y. Or that would be 12 because that is the sum of the two numbers. Now another one is their product is a maximum. So with that, the product is x times y. Now take note here. This one here is considered as the constraint equation. Your clue there in getting the constraint equation is that usually it has two variables. While this equation here is considered as our optimization equation. Why? Because most of the time it has three variables involved. Okay, now let's simplify our constraint equation here. So transferring x to the other side, we will end up with this. So with this, we can substitute y in this equation. So take note, our p here, so we have x. Take note, our y here is 12 minus x. So multiplying this, so multiply it with the terms inside, so 12x minus x squared. So with this, get the first derivative. So we end up with 12 minus 2x. So at this point, equate this to 0 and solve for x. So with that, our x is 6. So at this point, let's get the second derivative. So our first derivative is this one. To get the second derivative of this is 0. Derivative of negative 2x is negative 2. Since negative 2 is lesser than 0, so at this point, it has a relative maximum. So take note, what's required here is a maximum product. So take note, x is 6. So if our first number is 6, to get the other number, so that would be 12 minus 6, or simply it is 6. So therefore, the numbers are 6 and 6. So please take note of that. Okay, another. Now, if you have 260 meters of fencing materials, what should be the dimensions of the rectangular region if you have to maximize the area? So take note here, or in the first part of the sentence, you have here 260 meters of fencing material. So you're talking about perimeter here. So take note, perimeter is twice the length plus twice the width. So take note, the fencing materials is 260 meters. So substituting, you will end up with this. So again, this is your constraint equation. Okay, next. So you're talking about area here. So area of a rectangle is length times width. So again, this is the optimization equation because again, it has three variables. So let's simplify this one. Let's solve this in terms of the length. So transfer 2w to the other side. We end up with this. Divide the entire equation by 2. So our length here would be 130 minus w. So again, substitute here. So again, our width here is w. Our length here, substitute, it's 130 minus w. So multiply this one. So we end up with this. So at this point, we will get the first derivative. So derivative of this is 130. Derivative of this is negative 2w. So equate this equation to 0 and solve for w. So with this, our width is 65 meters. Now, getting the second derivative, so take note, we're talking about maximum. So our first derivative is here, second derivative is negative 2. Since negative 2 is lesser than 0, so at this point, it has a relative maximum. So take note of that. So take note, our width is 65 meters. So to get the length, so that would be 130 minus 65. Still, it is 65 meters. So take note of that. A rectangular garden is to be fenced off along the side of a river. No fence is needed along that side. There are 120 meters of fencing materials to be used. Find the dimensions of the garden with the largest area. Now take note of this. So we have here our rectangular garden. So that's where the river is. So with that, take note, we will not fence along the side. So we'll have 2 width and 1 length. So with this, our perimeter here would be length plus 2 width. So since we have here 120 as our fencing material, so L is plus 2W. So again, take note, this is our constraint equation. So since we're asked to find the largest area, so area of a rectangle is length times width. So let's simplify this one. So our length here is actually 120 minus 2W. So substituting here, so our width is W, our length is 120 minus 2W. So multiplying this, so we end up with this. So get the first derivative. So that would be 120 minus 4W. Now equate this to 0 and solve for W. So we end up with 30. So take note, our width here is 30 meters. So get the second derivative. So it's negative 4. So since negative 4 is lesser than 0, so it has a relative maximum. So take note, we're asked to find the largest as well. So since our width here is 30, so 30 and 30. So to get our length, so that would be 120 minus 60, so 60 meters. So the dimension of the rectangular garden here will be 30 meters by 60 meters. So please take note of that. Okay, another. A rectangular box is to be made from a piece of cardboard 24 centimeters long and 9 centimeters wide by cutting out identical squares from the 4 corners and turning up the sides. Find the volume of the largest rectangular box that can be formed. Now take note, when you sketch, this is the given. This is 24 centimeters long. This is 9 centimeters wide. So take note, we have to cut out this. So we don't know what will be its dimension. So we'll assume that this is S. So with this, so when you fold this up, so this will become our height. So this one here, instead of 24, it will be minus 2S. So that will be our length. And this width here will be subtracted by 2S because again, you cut out this S centimeters long. So take note of that. So again, this is our constraint equation because we have this variables here. So take note, we're asked to find the volume, and volume of a rectangular box or a rectangle is length times width times height. So this is our optimization equation. So substitute. So our length is 24 minus 2S. Our width is 9 minus 2S and S. So multiplying this one, we will end up with this. So at this point, get the first derivative. So that's 216 minus 132S plus 12S squared. So again, equate this to 0. So since we can divide the entire equation by 12, we end up with this. So factoring this, we will end up with S as 9 and S equals 2. So at this point, we'll go for 2. So take note, we cannot have S as 9 because this is already 9. So we cannot take out 9 from it. So we'll go for S. So our height here will be 2. So 2 centimeters. So our length is 24 minus 4. So that would be 20 cm. And for the width, that would be 5 centimeters. So since we're asked to find the largest volume, so the largest volume here is 20 times 5 times 2. So we end up with 200 centimeter cube. So please take note of that. Okay, another. Okay, determine the dimensions of the right circular cylinder of greatest volume that can be inscribed in a right circular cone of radius 6 centimeters and the height of 9 centimeters. Now take note, this is our right circular cone, and radius is 6 cm and the height is 9 centimeters. Now we need to inscribe a right circular cylinder. So with this is a radius and our height is also unknown. Now at this point, we can sketch a right triangle here and this one here. So getting our triangle. So with this will be R and this one here is 6. Now take note, this is the height of the cylinder, so it's h. Now take note, if this one here is 9, so at this point, this will be 9 minus h. At this point, we can form our proportion in which that will be r over 6 is equal to 9 minus h over 9. So simplifying this, cross multiply, so we end up with this. So solve for h. So we end up with 9 minus 3r over 2. So take note, this will be our constraint equation. Now, take note to find the volume of a right circular cylinder, that's pi r squared times the height. So substituting here our height with this, so we end up with this. So multiplying, we end up with this. So get the first derivative. So this will be our first derivative. So equate this to 0 and solve for r. So at this point, we end up with r equals 4. Now solving for the height of the cylinder. So that would be making use of this equation. So substitute r by 4. So we end up with 3. Now, getting the second derivative, so take note this is the first, so to get the second, so this would be 18 pi minus 9 pi r. So since our r is 4, substituting here, we end up with negative 18 pi. Since negative 18 pi is lesser than 0, so at this point, it has a relative maximum. So we're asked to find the greatest volume as well. So at this point, the height of the cylinder will be 3 centimeters and the radius is 4